Hello. Um, my name is Ryley Benavides. This is my lab 5 for CECS 225, section 2 of the lab. I put all of this Vivado stuff inside of my document, but I will show you that I have it done. Right now I have the simplified version with its test bench. I had that synthesis run, so the schematic looks like that. It has I'll show you guys. I'll show you more in the document. And the other schematic looks like that. And then the simulation. I'll just show you on the document I created. So, with the original equation, we started off with high fluid level, high temperature, high pressure, or low fluid level, high temperature, high weight, or low fluid level, low temperature, high pressure, low fluid level with low weight and high temperature. These are all and statements in between these, and then to make the whole equation, you put ors in between all of them. So basically, we just want an alarm to go off if any of these are 1. So yeah, 1 or 1 or 1 or 1. And the alarm will go off. Here's my truth table. I labeled all the, for L, all 0 and 1, L naught, T, T naught, etc. all the way to the end of the equation. I got these answers for the equations. Here's my simplification of this equation. Just this one's distributive, and then you have identity, and same thing on the left side, all the way till you get to the bottom. And this is the simplest form that I could come up with right here. The truth table for the simplified equation, if you look at these inputs right here, you'll see that the output will be the same for the same inputs, regardless of W, as we kind of simplified in this equation. Oh yeah, here's the cardinal maps, and then I made a circle right here, and I made a circle right here, and that simplifies to this. So for my original Verilog code, I defined all my inputs and my output, and assigned my output the equation, the original equation that I set up there. It's L and T and P, or not L and T and W, or not L and not T and P, or not L and not W and T. Here's my test bench. Setting up all the possible different combinations you can have, and when you run it, I should do these schematics right here. It has the AND gates and all the equations, and then the OR gates. My simplified, I did the same thing. I just assigned all the inputs, the output. I assigned X to the simplified form of the equation that I had, which was T and not L, or P and T, or P and not L. And these are what the schematics look like for that. This being the, not L, the ands between the T and L, the and between the P and T, the and between the P and L, and then the OR gates between those. And when you run the simulation for the original equation, if you have inputs 1 for T, 0 for P, 1 for L, 0 for W, you get an output of 0, which if you go all the way back up to the original, if you have a 1 for T, 0 for P, 1 for L, 0 for T, 1 for P, or 0 for P, 1 for L, and then a 0 for W, and you get 0. So this one right here. So it lines up, and then if you go back down to the simplified version, same inputs equal the same output, the timing is the same. Yes, the outputs match for all, and they match in the truth table. Yeah, if you go back up to the simplified, truth table, same thing. You had, what did we have? 1 for T, 0 for P, 1 for L, 0 for W. So if you look, you had 1 for T, 0 for P, 1 for L, and 0 for W. Make it 0. Since there's no W here, if you scroll back up to the top, you can see that in the one that had the 1 for T, 0 for P, 1 for L, and then 0 for W, which is right here. You can see that even after we change the 0 to a 1, it's the same output. So the simplified expression does not include W. Yeah. That is it.